Hello guys, this is Prime Concept. Now in this video, we'll be considering the concept of energy stored in a capacitor. Now we'll be looking at the relationship that we can use to determine the amount of energy a capacitor can actually store, right? Now if you have been following my videos, please do well to hit the subscribe button, like, comment, and then share with your friends so that they can also benefit. This is Prime Concept. Now let's go to the business for the day. Now we want to look at energy. Energy, of course, potential energy stored. Energy stored by a capacitor. Now we mentioned that a capacitor is actually an arrangement of two parallel plates. Now if you bring any two parallel conducting plates, those plates, of course, each of those plates naturally has a neutral charge, a net charge of 0. And if you bring them and then you connect their ends to a battery, so what would happen is that battery will begin to supply charge to the plates of the capacitor. The work done in increasing the potential or the charge on that capacitor plate is what we know as energy, or electric potential energy. So potential energy, electric potential energy, is the work done in increasing the charge on the plates of a capacitor from 0 to a value Q. That is energy or potential energy stored by a capacitor, right? Now before we do that, I want you to note something, that for a capacitor plate, one of the plates is usually at a charge of plus Q, and the other plate would be at a charge of minus Q. So you should know that at every point in time, the net charge on a capacitor plate is going to be what? 0. So you should take note of that. But that is by the way. Now, energy is the work done in increasing the charge on a capacitor from 0 to a value Q. So the work done in increasing the charge on a capacitor plate from 0 to a value Q is what we call the work done, or the energy stored in that capacitor. Now if you recall, work done W is actually equal to what? Is equal to the integral of V dq, right? Now we want to charge our capacitor from a value at the initial point. The charge on that capacitor is 0. We want to increase it from a value of 0 to a value of what? Q. Now with this, we can now find the work done, right? Now if you recall from what we've been doing since, we said that Q is actually CV. So that if I make V the subject, I would have that V is Q divided by what? C. So what I'm simply going to do, I'm going to replace my V with Q over C. So that my work done is equal to integral from charge 0 to charge Q. I'm going to replace this, so I'll have Q over C dq, right? Now whenever you're doing your integral, you should know that anything you have inside your integral that is a constant, you bring it out. So I have 1 over C is a constant, I'll bring it out, so that my work done becomes 1 over C integral from 0 to Q of Q dq. So this is what I would have. Now when you integrate Q, it's going to give you actually Q square over 2. Q square over 2, right? So I would have that my work done is actually 1 over C Q square over 2. So that you can write it in a better way. You can simply say that your work done, which is equal to potential energy U, is actually half Q square divided by what? C. So this is our first equation for work done, or electric potential energy, stored by a capacitor. Have Q square divided by what? C. Now we can still get other relationships for this, right? Now, if you still use the concept of Q, you still use Q equals CV. If you substitute Q for CV, if you substitute CV for Q, you will have that your potential energy is going to be half into CV, all what now? Square divided by C, right? So that this C would reduce one of the C here. And then you have that U is half. One C would cancel one, so you just have C, and you have V squared. So you have half CV squared. So this is another formula for potential energy. Then the third one, is I'm simply going to replace C, right? So if I replace C, I would have, okay, C is Q over V. So I would have that C is Q divided by V. So if I come back here and I replace C with that, what would I get? I would have that U becomes half in this equation, half C. Instead of C, I would write Q over V times what now? V squared, right? So that one V here would reduce one V. And then I would have that U is half QV. So this is my equation 3. So these are the 3 equations I can have for work done or potential energy stored by a capacitor. This is 1, this is 2, and this is 3. So any one of these 3 can be used to solve problems depending on what you are given and what you're trying to find, right? Now, you should know that potential energy or work done by a capacitor is actually measured in what? Joule, and is a scalar quantity. And the next thing we want to also consider in this video is the energy density. Energy density. So what we call energy density is energy stored by an electric field or in an electric field. That's what we call energy density. Energy density. So we denote that. I'll be denoting it with small letter U. So, but let me put D so you know that it's energy density. It's usually denoted with small letter U, while potential energy is denoted with capital U. So energy density is the energy stored per unit volume. So energy density is energy stored in an electric field per unit what? Volume. So let's look at how we can find that. If you recall, U, potential energy U, is equal to half CV square, right? Yes. Now what I'm going to do, I'm going to also recall that capacitance of a parallel plate capacitor C is equal to A epsilon naught divided by what? D. So this is formula for capacitance of a capacitor. Also, if you recall, V is also equal to what? ED. So I'm going to substitute these 2 equations into my potential energy equation so that I would have that U is half. Instead of C, what would I write now? I would write A this divided by D, right? Then instead of V, what would I write now? I would write ED all what? Square, right? So this is what I would have, so that U becomes half A epsilon naught divided by D, and I have E square D square. Now what do you notice from here? This D would fizzle one of the D's here, and you have just one D, right? So that you have U now becomes half epsilon naught. I'll write this, then I'll write my E square, then I have A, then I have one of the D's here. I have D because this would cancel one, you're left with one D. So this is what I would have. Now, if you also recall, so see what I'm going to do. I'm going to bring this AD under this, so that I would have that U divided by AD is going to be what? Half epsilon naught E squared, right? Now, what does AD represent? A is area and D is distance, right? Or the height. So what it means is that area times distance, what does it stand for? It stands for volume, right? So that we can now conclude that the energy per unit volume is now called U over AD is energy density. U over AD is energy density, where AD is what? Volume. So energy per unit volume is what we call energy density. So what is our formula for energy density? Our formula for energy density is now half epsilon naught E squared. So this is our formula for energy density, where E is electric field intensity. So E is electric field intensity, right? And what is the unit? Unit of energy density. Unit of energy density is joule per meter cube. The unit of energy density is what? Joule per meter cube. The unit of energy is what? Joule. So don't confuse these two things. So take note of this. In this video, we were able to analyze energy stored by a capacitor, right? Yes, we said we derived 3 formulas for the energy stored by a capacitor, and then we derived a 4th formula, which we call the formula for energy density. Now, I believe this concept is very clear. So if you have followed my video up to this point, please do well to hit the subscribe button, like, comment, and share with your friends so that they can also benefit from this. Remember, this is Prime Concept. Thank you.